In this video, I'm going to share the fundamental of PID control parameter tuning. There are two methods in basic PID control parameter tuning. The first method we call as a step test method, and the second method we call as a continuous cycling method. The step test method, or called as first order method, is very popular and using a simple experimental procedure. On the other hand, the continuous cycling method, or also known as the second order method, is also popular for online tuning method. This video we're going to focus on the step test method. Simple experiment have to be done for step test method, and the experiment have to be done in open loop mode. In this experiment, or in that particular experiment for step test method, we have to ensure that the process have to reach a steady state and the controller must be placed in manual mode. Changes in PV, which is the present value, from initial state to steady state is resulting from the input excitation of the controller. Several important things for step test method: the output response or present value obtained from the output is the result of the unit step input response in step test experiment. The step input excitation will exhibit the S-shaped curve output if the plant involves neither integrator nor dominant complex conjugate poles. The S-shaped curve characterized by two constants, whereby this S-shaped curve is basically the dynamic of the present value or PV, and two constants that we are concerned on is the time delay, which is theta, and the time constant, which is tau. In order to get those two values, we have to find the maximum tangent line at the inflection point of the S-shaped curve. The intersection of the tangent line to the time axis will indicate T0. The intersection of the tangent line to the steady state output, which is on the top side of the output line, will indicate T1. Simple analysis from T0 and T1 will get time constant and time delay. And from time constant and time delay, we can then construct the first order system with transport lag, which will be given by the transfer function Cs over Rs, which is normally written as K times exponential of minus time delay S over tau S plus 1. As mentioned earlier, the step test method to find the tuning parameter of the PID have to be done in open loop response. And the step test given to the plant is basically the input excitation to the plant, and the result from the input excitation to the plant will characterize the S-shaped curve of PV. From this S-shaped curve of PV, we're going to find the maximum tangent line, and that maximum tangent line will be based on the one inflection point. The crossing from the tangent line, the crossing between the tangent line and time axis, we can get T0, and the crossing between tangent line to the steady state output, we can get T1. The time deviation between T0 and T1 is called time constant tau, and the time given from inertial changes from input excitation to T0 is called time lag or time delay, denoted by theta or Td. Time constant and time delay is very useful to determine the parameter of PID controller, whether we as a user are going to use proportional control only, proportional plus integral control, or proportional plus integral plus derivative control. From this table, we can see that we have parameter tau and theta, whereby tau is time constant and theta is the time delay. For instance, if we as a user, and based on the system characteristic, we decide to use proportional control only, so from the previous system dynamic, we can see that we have time delay and time constant, so we can apply the value to get the proportional gain, and then by setting the time integral to a large number and derivative time to 0. For proportional plus integral, we have to multiply time constant with 0.9 divided by theta, which is time delay, and integral time is set by time delay divided by 0.3. Meanwhile, for proportional, integral, and derivative, we have to multiply time constant with 1.2 over time delay. For time integral, we have to multiply time delay with 2, and the derivative time we have to times 0.5 with the time delay. Consider a temperature process for a heat exchanger. In this heat exchanger example, we have a boiler. The function of this boiler is to provide hot steam to the vessel. This hot steam is manipulated by a control valve, and this control valve is controlled by a temperature indicator controller. The product for this temperature process is measured using temperature transmitter 811. In order to excite the system with a step response, we have to set the manual mode for temperature indicator controller. So this is already manual mode, so in this faceplate we can change to manual or auto mode. So remain manual mode. In order to turn on the heater on the boiler, just press this button. So on this faceplate, we can change run to turn on the heater, stop to stop the heater. So now we're going to heat up the boiler, press run. So the boiler is running and trying to supply the hot steam to the vessel. This control valve is fully closed, and the product temperature is currently 33 degrees Celsius. Click the process history view to show the process trending. Observe that we have the red line for process value or for present value, we have blue line for set point, and we have black line for output, which is this is the manipulated variable for control valve, providing the step input to the manipulated variable, which is this control valve, by changing from 0% to 100%, and we're going to monitor the PV for this temperature process. This black line is representing the changes that we apply to the control valve, which is the control output. Observe the red line. The red line is already climbing, means the temperature is increasing. So observe that this temperature is increasing. Initially it was 33 degrees Celsius and currently it's become 79 degrees Celsius, and we're going to wait PV reach steady state. The time deviation from control output changes to this corner, which we can measure later. We can call it as a time delay. PV is climbing and slowly going towards steady state. If we look at the graphic, so the temperature now is currently 120.6 degrees Celsius. It's quite hot. It's very hot. And I think it's going to settle around 121 degrees Celsius, okay, or 122 degrees Celsius. So more or less, it's already reached a steady state value, which is around 122 to 123 degrees Celsius. Assume that the steady state now is 122.6, or I think it's easier 123 degrees Celsius. Later in this video, I'm going to show you how can we analyze this curve, the rate curve, so we can get few parameters, several parameters, including time constant and time delay, whereby those value is very useful for defining or to determine the PID control parameter for the proportional, integral, and derivative. Okay, this is the system response from previous experiment done in delta V. Data from delta V has been taken out and processed in another software in order to get better view. And using another software, the inflection point is calculated, and the inflection point is given by at time t equal to 30 seconds and at PV is equal to 41 degrees Celsius. Another important information that been calculated using that software is the maximum gradient for this inflection point. This maximum gradient represents the slope gradient for the maximum tangent line. And the maximum tangent line and the gradient for the maximum tangent line is given by 3.2217. Also observe that the initial temperature for this experiment is 33 degrees Celsius. And the steady state output in this experiment is 123 degrees Celsius. Next, we have to draw the tangent line to get intersection between the tangent line to the initial point, which is 33 degrees Celsius. And we also have to sketch that tangent line to get the intersection with steady state output 123 degrees Celsius. Using y equal to mx plus c, where m is equal to 3.2217, to get the value of c, whereby value of c is representing the intersection of tangent line with y-axis. Substitute the value of y with value of PV 41 degrees Celsius, value of m with 3.2217, value of x with t is equal to 30 seconds, then we can get c. Therefore, we got value c, which is equal to negative 55.651. So we can get general equation for the tangent line is equal to, then using this general equation, we can find intersection of the tangent line with the initial state of the air temperature plant. So when value PV is equal to 33 degrees Celsius, we can get the intersection, which is the time at 33 degrees Celsius. Then we can also calculate the time when the tangent line intersect with the steady state output, which is at PV is equal to 123 degrees Celsius. So the first intersection is when PV is equal to 33 degrees Celsius and time when PV is equal to 33 degrees Celsius is 27.517 seconds. So it is somewhere here. And when PV is at 123 degrees Celsius, which is at the steady state output, the time is 55.452 seconds. So it's somewhere here. So the maximum tangent line is basically somewhere at this, okay? That is the maximum tangent line. But the more important thing is we're going to calculate the time constant and time delay, whereby these two parameters will be used to determine the proportional gain, integral gain, and derivative gain for our controller. So time delay is straightforward. Time delay is given by 27.517 seconds. So theta is the time delay. Meanwhile, for time constant is given by the deviation between time delay and this time is intersection between the tangent line with the steady state out. For time constant tau is given by 55.452 seconds minus 27.517. So it is equal to 27.935 seconds. So from the calculation, we can get that theta is given by 27.517 and tau is given by 27.935. So we can plug both value into this table to get proportional or proportional plus integral or proportional plus integral plus derivative if you want to use the controller. So assume that we're going to use PI controller. So for PI controller, Kp is given by 0.9 times 27.935 over 27.517. So it is approximately 0.5, and integral time is given by 27.517 over 0.3. So it is approximately 96. Proportional gain is equivalent to 0.5 and integral time is 92 seconds, and we can plug this value, the proportional gain and integral gain, into our controller, which is built in our delta V system.